Welcome, and thank you all for coming here. Vanderlei, Bagnato, and I are very pleased to have the opportunity to tell you this evening, in this next hour, about the International System of Units, le Système International d'Unité, the metric system, the system we all use all over the world to measure things, but in particular about the big changes that are going to occur. And as you heard, this talk is brought to you in part by the International Union of Pure and Applied Physics, of which Vanderlei and I were members of the commission that has to do with units. And I might also say that IUPAP is one of the sponsors of this meeting at ICAP, and we're very pleased to be part of ICAP and be able to bring you this.
And that's the only place where I was the boss of Bill. Everywhere else, he's my boss.
So, Vanderlei?
Yes, we would like to thank some of the students in Brazil that helped to construct watt balance that we're going to demonstrate to you, which will be how the kilo will be realized. And Daniel is here, the other students are in Brazil, and many people helped to bring some bags carrying the demonstrations that you're going to see. So we want to thank them in advance, okay?
And we should also say, indeed. And we should also say that Daniel is now a member of Commission C2, so he's working internationally to keep up the business of units for all of us. So we are going to be talking about the metric system, the International System of Units. And this is a system that allows us to measure essentially anything. All of these units, the kilogram, the meter, the second, the ampere, and the others, are what we call the base units. And combinations of them allow us to express any of the physical quantities that we want to, quantities like work and velocity, for example. Throughout history, people have been concerned about measurement. In fact, I think measurement has been a part of our human culture since the beginning of human culture. Ancient people needed to measure things just as we do. Whenever you measure something, you're always comparing the thing you're measuring to some sort of a standard. If you want to measure the length of a table, then you're comparing the length of that table to the meter stick or the tape measure that you use to measure it. In ancient Egypt, the people who were building the pyramids compared the size of their stone blocks to the length of the pharaoh's forearm. That was the standard called a cubit. People in ancient Babylonia made stone weights, and they compared these weights to the weight of a coin made of precious metal. And one of these sizes of weight, I forget which one, is called a shekel. And that's where we get the name shekel for money in general. Ancient people in England made stone observatories that allowed them to measure time on a seasonal basis. And the rotation of the earth around the sun was the standard, even though they didn't understand that was what was happening. And today, we still need units of measurement. We need units of measurement that are accurate, that are convenient, and that are uniform throughout the world. And the International System of Units gives us that, with 7 base units from which all the other units can be derived. And today, we're going to describe and we're going to demonstrate how some of the units of the SI are defined. We're going to give a little bit of history of how they came to be what they are. And most exciting, we're going to talk about the new SI and the changes that are happening within the next year. So here's the SI again, all the base units, the kilogram, the meter, the second, the ampere, the Kelvin, the mole, and the candela are the base units of the SI. And we're going to be concentrating on these 4, the kilogram, the meter, the second, and the ampere. Now, in order to understand the revolutionary changes that are about to come in the International System of Units, we're going to examine how one of those units, time, has changed over history. So, with apologies to Stephen Hawking, we are going to offer a brief history of time. So, the second. We've been concerned about time since the beginning of human time. In ancient days, people worried about the seasons and planting, and they worried about things that were happening from one day to the next. And in modern society, we need even more accurate measures of time. The first and longest lasting definition of time was based on the rotating Earth. Ancient people didn't know that the Earth was rotating, but they saw the sun rise and set every day, and that allowed them to tick off days. And so the day was referred to a standard, namely the rising of the sun, which was related to the rotation of the Earth. In later times, people became more sophisticated, and they made things like sundials. They made things like pendulum clocks that allowed us to achieve even greater accuracy. But let's look at some pendulum stuff.
I think it's time for me to start work. We're going to make some demonstration with a pendulum. I think everybody has already played with a pendulum. It's the oldest experiment in time measurement. Galileo did 400 years ago. And here we have a pendulum, and I'm going to tell you a few things about the pendulum which are essential if we're going to use a pendulum to measure time. Okay? Well, we all know that pendulum has a periodic motion, so this round trip is what we use to measure time, right? And there are a few things about pendulum that some of you know, but some of you do not know. And the first thing that's important is the period, which is the time of the round trip of a pendulum, do not depend on the mass, which is a good news, right? Because it doesn't matter how you make the pendulum, if you somehow keep the length, you're going to always have the same time. So here we're going to do a demonstration. I have two weights, a light one and a heavy one, and we have to show to you that they tick at the same period. So we're going to send the bolt, and as you can see, they have the same round trip time, right? So it is independent on the mass. So it's good. You can use a small stone, a big stone to make a pendulum, and they always going to have the same thing. Now, it is dependent on the length. So if I multiply by 4 the length of a pendulum, I realize that this period of oscillation multiplied by 2. So this is a hint that depends on the root square of this length, which we know. And this is for you to see. If you can count who is going faster, you're going to see that the short one, right? The long one is going, and the short one is going, is kicking more. Okay, now, pendulum is nice, independent on the mass, depend very much on the length. And if we make the length independent of the mass around 25 centimeters, it has a round trip exactly of 1 second. So if you have a clock, you can see that this is going like a second. I can move the camera a little bit here, so you can see that this is like a second. So the bad news about the pendulum is that everything will affect the length. But the good news is the pendulum helps us to really measure time in short period. With the pendulum, we could be able to measure 1 second, not the rotation of the Earth. So we introduce the division of time using the pendulum, and it survives for a century. Right, Bill?
Exactly. Let's go back to the presentation. So using pendulum clocks and correcting and compensating for these problems with changing the length of the pendulum, people were able to make really precise clocks. And that allowed us to divide the day not just into hours, but into minutes and seconds. And until 1960, for centuries and centuries, the second was defined as being 1 over 24 times 60 times 60 of a day. That is 1 over 86,400 of the mean solar day, the time that it takes for the Earth to go around once relative to the sun. The trouble was that the mean solar day definition was left to the astronomers. And by the beginning of the 20th century, because people made incredibly accurate pendulum clocks, it was possible to see that the rotation of the Earth itself was not constant. And yet the very definition of time, the definition of what a second was tied to the rotation of the Earth. And people knew that the rotation of the Earth was not itself constant. This meant that our definition of time itself was something that changed with time, and this was intolerable. And so, well, I mean, think about it. You don't want a standard of measurement to be different from one day to the next, and that was what was happening. So, by 1960, people decided they needed to change the definition of the second. So they changed the definition of the second to be 1 over 31 million whatever of the tropical year 1900. Now, this is great because the length of the year 1900 doesn't change, but it's really hard to measure it today. And so this wasn't the most wonderful definition. So we had to have another definition. And the new definition was really a beautiful definition. They wanted to have something that would never change and something that would be accessible to everybody. And the answer was atoms. Every atom has certain energy levels, and the separation between those energy levels corresponds to a frequency. And that frequency can be used as the ticking frequency of a clock, and can be used to define what we mean by a second. Now, one of the great things about atoms is that every atom of the same kind, say cesium-133, which should be on here somewhere but isn't, every atom of cesium-133 in the entire universe is absolutely identical to every other atom. And that's one of the reasons why they make such great clocks, is because it doesn't matter where you got your cesium, it's going to keep the same time as everybody else's cesium. And so in 1964, they changed the definition of the second to be that number of oscillations of the radiation corresponding to the transition between two states of the cesium atom. Now, the way it works, roughly speaking, to make an atomic clock is you've got an atom. Say here's a cartoon of an atom that has two possible places where the atom can be in the lower energy state or the upper energy state, and you shine microwaves in at the atoms, and if the microwaves have just the right frequency, it'll excite the atom. Well, let's see how this actually works in an experiment where we're not going to use a real atom, and we're not going to use microwaves. We're going to use water waves, and we're going to use a wonderful model for an atom that Vanderlei and his colleagues have put together.
Yeah, the challenge here will be to show to you how the atomic clock works, how an atom works as well, without seeing the atom, without seeing anything. So, you know, microwave is electromagnetic wave. You know, we have electrical and magnetic field going up and down. And everything that we do in time is related to oscillations. So we cannot see very well the microwave oscillations, but we can see water. So we're going to reproduce this with water. So here we have a water tank, and as soon as my system says yes, we're going to start. I'm producing water waves. This means up and down. The water is not being transported, only the energy that I'm generating. I have here an oscillator that oscillates and generates the waves. And that wave propagates. It has a specific frequency. I can change the frequency here, you see. There are something we're going to speak later, which is the relation between the frequency and the space between those waves. But we produce waves, and we can produce those waves the frequency we want. Now, as Bill was saying, we cannot see the atom as well, but to make a clock, we need to have an atom to excite with this. And excite means the wave carry energies, and we shut this energy in the atom, and the atom will acquire this energy. We don't have an atom here, but we have an equivalent as well, which is my oscillator. So as you can see there, I have my atom, which is a mass connected to a spring, and it can acquire energy exactly like the atom. What is the oscillation here? Just roughly speaking, will be like the charge oscillating in the atom, or doesn't matter. We can couple energy from the waves to this oscillator. So as you can see, you know, if I increase the frequency, just pay attention to the mass there. It is scattering a few waves, but it's not oscillating. But if I start to change the frequency, there will be one specific frequency where that guy starts to oscillate. If I go too fast, it doesn't oscillate. So he is too fast, stop oscillation. If I go too slow, stop oscillation as well. I needed the right frequency. You see, this mechanism of coupling energy to the atom, because the atom is like an oscillator, roughly speaking, is called resonance. And we need a specific frequency to excite the atom, to put energy in the atom. And I have an oscillator, I have an atom. The atom will always oscillate with a specific frequency. And I am the controller. I can control the oscillator. So I can couple energy or not. If I have a reader here that will read this frequency, which is how many waves I'm producing per unit of time, you're going to see that by looking the oscillation of the atoms, I can always be in the right frequency. Atoms do not change their frequency, as Bill said, but oscillators that we make, they change. But we need an oscillator. So we use the atom to verify if the frequency we have is the correct one or not. So doing this resonance, we know exactly that we always have the same frequency there. And then I adjust, and if I can extract this frequency here, I will have a precision very close to the precision of the atoms. And that's how we can get a very precise frequency, which inverse is the time that we use to define the second. Now, just pay attention to one thing. I shine waves on my atom, and the atom takes this energy, but then gives away. If you see, there are some waves coming to everywhere, which are the atom radiating, and this we're going to see further on in the lecture in the real molecules in the cell. Okay, Bill, I think we have shown how a clock works.
Okay, let's go back to the computer. Okay, so that's the general idea. We keep adjusting the frequency of the microwaves until it's just right to excite the atoms, just as Vanderlei was adjusting the frequency of the water waves, so it was just right to excite the oscillator. And clocks based on this principle, with cesium, the atom that is used to define what we mean by a second, and cooled to temperatures below 1/1,000,000th of a degree, and I wish we had time to tell you that story, but we don't, of how we can get atoms colder than 1/1,000,000th of a degree above absolute zero. These clocks are keeping time to about 1 part in 10 to the 16. That is, I'm trying to think this through, that is 10,000 million million. 1 part in 10,000 million million. These things are really good. But different atoms ticking at even higher frequencies get even better results. They're not cesium, so they're not the legal definition, but they probably will be someday. This is Junyi in his laboratory at Gila in Boulder, Colorado, and using strontium atoms, he's made a clock that's good to 2 × 10 to the minus 18. Now, as of yesterday, I thought this was the best clock ever, but we heard today at ICAP that there's an even better clock in Boulder. David Hume has a poster, number 21, if you still want to go see it, where with a single ion, this accuracy is 9 × 10 to the minus 19. So that means it's better than 1 part in a billion billion. It's just astounding. This was done in the group that Dave Wineland founded at NIST in Boulder, and the results have just been astounding. So we have had a real revolution in time that came from the fact that we changed the definition of time from this inconstant Earth rotation to atomic clocks. Has produced amazing accuracy, now better than 1 second in the age of the universe. That's how good these clocks are. And it's because the atomic frequency is fixed by the unchanging laws of nature, so we can get better and better at doing it, and we know it's always going to be stable. Now what we're going to do is to look at a similar story for length. So, the meter. So we had a brief history of time, now we're going to have a short history of length. So, length has been important since ancient times. People constructed things like the pyramids in ancient times, and modern industry requires an increasing precision and accuracy all the time. An early approach to length was to use the body as the standard. So, you had the cubit, you had a yard, you had a fathom, a foot. This was convenient, but it wasn't very consistent. If you were buying cloth from a merchant who had short arms, you were not going to get as good a deal as if you were buying cloth from a merchant that had long arms. And so this was not a very wonderful situation. So one of the things people did was they turned to nature itself, a very modern idea. The barleycorn inch. At one time in England, an inch was equal to the length of 3 barley seeds. And this was wonderful because it turns out that the dimensions of these barley seeds is really consistent. Except maybe if you have a growing season where there isn't as much rain or there's more rain, it might change from season to season. So that's not so wonderful. Another ancient approach was surprisingly modern. The ancient Egyptians used as their standard the size of the pharaoh's forearm, but they realized that from one pharaoh to the next, this might not be the same. So they made a granite copy of the length of the pharaoh's forearm. And end to end on that piece of granite was the length of a royal cubit. And the people who were building the pyramids had wooden sticks that were that length. And they used those to compare to the length of their stones. And they had to come and calibrate their wooden standards against the primary standard, the granite standard. And if they didn't do it, the penalty was death. Well, for someone interested in metrology, it's good to see that these ancient people were taking things seriously. But it really is a very modern approach because we often have primary standards and then we have secondary standards that get compared against the primary standards, and we're going to see how that works in just a little bit. The Egyptians did amazingly well. A tiny fraction of a percent for the baseline. The things were square to 12 arc seconds. They were just amazing. Now comes the French Revolution and a different philosophy about measurement. The idea was to make a measurement system that was really logical, one that we still use today, in which the divisions are factors of 10. And the idea was it was going to be based on a new unit of length called the meter, which was supposed to be the measure of all things. And in the spirit of equality and fraternity, it should be available to everybody. So they decided, in this spirit of making it available to everybody, that the meter should be 1/10,000,000th of the distance from the North Pole to the equator along a meridian that runs through Paris. Now, so in order to get this number, they sent out 2 astronomers, Joseph Delambre and Pierre Mequin, with Delambre going north from Paris and Mequin going south from Paris. And the northernmost place that they surveyed was Dunkirk, and the southernmost place they surveyed was Barcelona. So Mequin, and this is a plaque that you can see somewhere here in Barcelona that commemorates Mequin's measurement of the meridian. Here's a blow-up of that previous thing. You can see Barcelona here. The last measurement, the most southern measurement, was made at Montjuic. And measurements were also made at Montserrat, names that are familiar to most of you. Here is where Mequin made his southernmost measurement at the Castello of Montjuic. And, they had a lot of trouble because they were constantly being thrown in jail because there was a war going on, and they always wanted to get to the highest point and had this funny apparatus, and people kept throwing them in jail. But they finally did it, and they took the measurements back to the French Academy. And because it's so difficult, it took them years to do this surveying, they preserved the length of the meter in this bar called the meter of the archives. And then other people would have similar bars, and they would compare it against the end-to-end distance of the meter of the archives in pretty much the same way as was done with the ancient Egyptians. Now, forward a little bit, in 1875, a group of countries from all over the world got together and agreed that they would adopt the same system of measurement, the metric system, throughout the entire world. And they agreed that they would make a new standard of length. This time, instead of being end-to-end, it was the distance between two scratches on a platinum iridium rod. And that distance was a meter. And everyone agreed that was a meter, that they would use that meter in all of their measurements. Those countries, by the way, included the United States of America, agreed to be metric in 1875. And this was a better standard because you didn't have to touch the ends to measure the meter, so there wasn't a danger of wearing it out. But then people realized that measuring the distance between two scratches was not so easy, because where was the middle of the scratch? I mean, after all, it's a scratch. And when you look at it with a microscope, for the level of precision they needed to use, that scratch was not something that was unambiguous. And so they decided to use other methods for measuring length. And we're going to see in a moment how the wavelength of light can be used as a standard for measurement. In the 19th century, people understood that light was a wave, and they started to make instruments, interferometers, that could measure length using the wave nature of the light. So you have a light source here, and it's split up, and you have a mirror that moves, and every time this mirror moves, it changes the interference pattern. That is, it changes where the light waves are lining up, so the crests of one beam match with the crests of another, and you get a light spot, and where the crest of one wave matches with the trough of another wave, and you get a dark place. And by moving this mirror just a tiny fraction of the wavelength of light, you can change this pattern. So let's see how that works in practice.
In the interferometer?
In an interferometer right here.
Okay, so we have here a real interferometer. You know, we work in atomic physics and all. So this is a laser, and then the laser is divided in two parts. The laser beam is divided in two, and as you saw, the laser are like those waves, and when we divide, we have two waves going different paths. And if they are equal paths, then the wave will recombine, and maximums will be on the maximums and minimums on the minimum. But if there is a small delay in one of those paths, then whatever the wave wants to go up, the other one wants to go down, and then they annihilate. And then you have a minimum, you have dark. The result of this is a collection of fringes, as Bill was showing. And this fringe, each movement from one fringe to the other is equivalent to the wavelength of light, which is tiny. You know, we are talking about, for this case, something like 600 nanometers. And as we touch the mirror, we can make one of the arms to go a little further than the other. And then when you see one fringe moving from one position to the next, where was the last one, means that the distance that we move is 1/3 of a micrometer. And a micrometer is 1/1,000,000 of meter. So by looking this, we are able, using the finger, to produce a displacement which is 1/3 of 1,000,000 of the meter. So that's the precision, kind of precision you can have. Of course, you can see a little fraction of those motions. So interferometry is the way to measure really very small distance, as we're going to see later on.
And the distance between these fringes, the amount by which a fringe moves, when you change the path length by a half a wavelength, is about the limit of resolution of the best optical microscopes. So this is automatically better than what you could do by looking at a scratch on a meter stick. And so let's go back to the... And so what happened was, in 1960, so it took a long time to change the definition. In 1960, the definition of the meter was made a certain number of wavelengths of the radiation coming from a discharge lamp with krypton 86 in it. 1960. So from 1875 to 1960, the definition of the meter was the distance between two scratches on a metal bar. And now in 1960, the year the laser was invented, they defined it as a certain number of wavelengths of the radiation coming from this discharge lamp. But this was the year the laser was invented, and it wasn't long before people were making lasers that put out light that had a higher purity. That means it had just a single wavelength, a much higher purity than the light coming from this lamp. The light coming from the lamp turned out to be a mixture of a number of different wavelengths, and it wasn't possible to tell what the actual wavelength of the lamp was. And soon, people were making measurements of length that were not in terms of the legal definition of the meter, that were instead in terms of a de facto definition of the length of a laser that was stabilized to a transition in molecular iodine. So this is what we call a de facto, an unofficial standard of length. It was not the legal standard of length, but everyone was using it because it was so much better than the legal standard of length. And it was based on locking a laser to a transition in molecular iodine. Let's see how that works.
Yeah, so we're going to use the same laser, but now we have a cell which contains iodine. And iodine has a specific transition. So like I did with the arm in the water tank, if we put in the right frequency, you see light shining. If you remember when I was shining waves on that atom, you see some light, some waves coming out, uniformly distribute, isotropically distribute. This is what we see here. The laser that you don't see very well if you go out of the frequency. If we move out of the frequency a little bit, you don't see the beam. But when the beam is exactly on a frequency that excites that molecule, that transition, you see that light coming out. What we normally do is we keep the frequency. You know, I am now the electronics of my locking system. I can come here and precisely keep the laser in that transition. When I do that, the wavelength of this laser is precise what is determined by that transition, like in the krypton. And once I have that, I can now count the fringes until I add enough to make the meter. And that's what Bill was describing.
So let's go back to the computer. And so what happened was people were using this iodine stabilized laser as a de facto standard of length. And it was clear to everyone that the definition of length needed to be changed, because you couldn't have everybody using a definition of length that was not the agreed upon legal definition of length. And you might think that the obvious thing to do, and it was the obvious thing to do, was to simply redefine the meter to be a certain number of wavelengths of this iodine-stabilized laser. That would have been the logical and simple thing to do, but that is not what they did. And thank heavens that is not what they did. Instead, what they did was define the speed of light. Now, what does that do for you? This is the current definition of the meter. The meter is the length of path traveled by light during a certain interval of time. And we know time very well from the cesium clock. But essentially what this does is it defines the speed of light. Now, why is this so wonderful? We have this general relationship. The speed of light is equal to the wavelength of light times its frequency. That means if you've got any light, doesn't matter what color it is, what its frequency is, if we can measure its frequency, and we've already defined the speed of light, then we know exactly what its wavelength is, and we can use it as a ruler. So we're not limited to one particular laser, stabilized to one particular molecular transition. Any laser that we can measure the frequency of is going to be good. The speed of light is the same for every color, and so if somebody makes a better laser, wonderful. We immediately get the advantage of that better laser using exactly the same definition. Somebody makes a better measurement of the frequency, we immediately get a better definition of the meter, a better realization of the meter by using the same definition. In 2005, these three guys got the Nobel Prize given to Jan Hall and Ted Hench. Both Ted and Roy are here at this meeting. And the Nobel Prize for Hall and Hench was for learning how to do a better job of measuring the frequency of light. And that improvement was immediately able to be used in making a better realization of the meter. So,
Bill, before going to the kilo, we can show in a wave what is the wavelength and how
sure,
we add
absolutely.
up.
That's right.
Show.
We didn't do that yet. Let's do that.
Sometimes you have to interrupt your boss.
Sometimes we get so excited
we're
about
going
what we're
to do
doing,
the
we
following.
forget.
We're going to produce the wave. You know, it is like light for us here. So as you can see, if you can more or less observe, when I increase the frequency, I'm changing the frequency of the wave here, but the speed is not changed. You know, so if I freeze the image now, just take one image. You see that this distance here is a constant of that wave, and that's the wavelength, and that's what we're using now to define the length. But the important is to observe that the speed of light is now defined, and we need that definition, because if we have that defined, if we can measure well frequency, we have very well the length. And once we have that length, we can construct any size we want, including the meter, by just adding in the interferometer.
And so, since 1983, the speed of light has been defined. Let's go back to the, so since 1983, the speed of light has been defined. If you think your students are doing an experiment to measure the speed of light, you should tell them that they cannot. In fact, it will be illegal to measure the speed of light because it's defined. What they're really doing is realizing the meter. So now we've had this wonderful revolution in timekeeping by defining time based on some unchanging properties of nature. We've defined length by defining the speed of light, an unchanging property of nature. But what about the kilogram? Well, let's have a light history of mass. As we saw before, in ancient times, objects were the mass standards, and these objects were compared against coins, for example. And of course, a lot of people tried to cheat by making false copies of these standards, and such cheating was strongly condemned. In fact, the book of Proverbs in the Hebrew Bible says, "A false balance is an abomination to the Lord, but a just weight is his delight." So being serious about metrology goes back a really long way. And throughout history, some of the most famous scientists, physicists, and chemists have been concerned with mass. Newton taught us about the way that masses move when subject to forces, about the way that mass gives us gravity. Lavoisier taught us about the conservation of mass and did one of the early realizations of the standard of mass using a liter of water. Einstein taught us that mass curves space-time. But mass is also important for economy and for the society. Here's an 18th century drawing of a woman weighing out something that's to be sold using a balance, comparing the weight of some product to the weight of some standard. If you go to the grocery store, you may buy fruits and vegetables by the kilo. And this is 6 reals for a kilo of tomatoes. And you want to be sure that you're really getting a kilo. And if you're worried about your weight, you want to make sure that your bathroom scale is measuring things in kilos. So we're really concerned about mass in all sorts of ways. And in the spirit of the French Revolution of universality, around 1793, the kilogram was defined as the mass of a cubic deciliter, which is to say a liter of water. So you have a cube that's 10 centimeters on a side, and if that's filled with water, then the weight of the water, the mass of the water is 1 kilogram. And Lavoisier was the one who made that determination. Now it turns out, It's not that easy to do. To fill up a volume and make it exactly a liter is not very easy. Plus, the density of water changes with temperature. And so even though they defined what the temperature should be, it wasn't so easy to make this measurement. And so they decided to follow a process that we've seen again and again. They took that definition of the kilogram based on water, and then they made a platinum artifact standard that was as close to the water definition of the kilogram as possible, and they made that new artifact the standard. Here's a picture of the platinum cylinder and its case. This is called the Kilogram of the Archives, made in 1799. And let me just put on,
yeah, you have to put
we've
the
got to
gloves.
put on these white gloves. We're going to show
It
you.
has to be white.
Because you wouldn't want to have any dirt. So,
We have here the artifact, in fact.
let's bring this up here so that maybe people can see it a little bit better.
I hope we don't drop.
This thing is a replica. Very few people have such a thing. This is what the kilogram of the archives looks like. Now, we're wearing white gloves to handle this because if we leave a fingerprint on this thing, then all of you get lighter. Because this is a kilogram, or at least the real thing. So maybe some of you would like that. But you see, metrologists absolutely reject the idea that our standard should change because the standard is the definition of the kilogram. And this is what it looks like. And then a little bit later, as we're going to see, now where did I put the clicker? So this was 1799. So in 1875, at the Convention du Mètre, they decided to make a new kind of kilogram, and a few years later, they made a kilogram that looks exactly like the one you were seeing there. It's called the International Prototype Kilogram, made of platinum iridium. And that is still the definition of the kilogram today. The current definition of the kilogram is that it is the mass of the international prototype of the kilogram, which is that object that is held in a vault somewhere in the basement of the International Bureau of Weights and Measures outside of Paris. So think about this, my friends. We are in the 21st century, and we are using a definition of mass that was established in the 19th century based upon an artifact that was made in the 18th century. This idea is so scandalous that in America, in the United States, newspaper cartoon strips make fun of it. So here's a cartoon. A little girl is in her science class and she asks her science teacher, am I right that we've redefined the meter to be the distance that light travels in a certain length of time? And the science teacher says yes, because the previous definition based on the size of the Earth was inaccurate. And then she says, and we've similarly redefined the second, which used to be a certain fraction of a day, and now we've defined it in terms of oscillations of the cesium atom. And the science teacher says, yes, very good. And then she says, why haven't we changed the definition of the kilogram? And he says, we haven't. The official definition is still the mass of the international prototype kilogram, an actual lump of stuff that's stored somewhere. Why? That's so unscientific. Exactly. What if someone sneaked in and shaved off a piece? And the science teacher says, I need to lie down. And the little girl says, I told you there was ways of getting to him. Well, you see, our whole lecture is right here in this comic strip. Nobody has sneaked in and shaved a piece off the international prototype kilogram, but its mass is changing nevertheless. Over history, we have seen the ways in which the various copies, everyone who signed the Treaty of the Meter got a copy of the kilogram. And we've measured those copies against the international prototype kilogram over the years, and they have changed, some of them, by more than 100 micrograms. That's more than a part in 10 to the 7. And that's an intolerable change for a metrologist. Now, of course, Legally, the International Prototype Kilogram cannot change because it is a kilogram. But this is just like that horrible situation when we had the definition of the second changing because the Earth's rotation wasn't constant. Now we have the definition of the kilogram changing because the kilogram accumulates dirt and the way in which they wash off the dirt isn't perfectly consistent. And it seems like among all the standards that unluckily, the International Prototype Kilogram seems to be one of the worst. So what are we going to do? This scandalous situation has got to be fixed. And what we're going to do is fix it using the same principle that we've used to fix the meter. We're going to define a value of one of the fundamental constants of nature. So to define the meter, we define the speed of light. What are we going to define in order to fix the kilogram?
Okay, well, see, he always gives me the hard job. So the constant that was chosen to be fixed to define the new kilo is the Planck's constant. You know, Planck's constant is a constant related to the energy of a photon, which is a package of energy in the light, and has a value, and has in the units the kilo, and it's being chosen to...
We're 10 minutes behind where we should be.
Yeah. Is everybody tired enough? We should rush out, or we can go and explain to you how the kilo will be done. We can? Okay. So just be patient, because we're going to demonstrate the realization of the new kilo. And the whole idea, we made this diagram because defining constants in nature and associate with unit has a principle on it, because we have to measure the constant. So normally we use something like the kilo, we're using the kilo to define the constant. So we use the kilo and we measure well Planck's constant, for instance. But once we measure as well as we can, we define. And then we go back here, and from now on, the kilo will be defined based on the definition of the constant. So it looks like a circle, right? But it makes sense, as you're going to see. Okay, so the Planck constant is what we chose. And defining something and realizing something is a little bit different. We can define the kilo based on the Planck constant, but then we have to realize. Anybody that wants a kilo has to have a way of getting, right, the real mass, like the artifact that Bill showed to you. And the way to do that, one of the ways at least, is using what we call the Watt or Gibbel balance. This is a balance that do not equilibrate mass, equilibrate power. So I'm going to demonstrate to you with a few slides, very simple formulas, why is this equilibrating power and how the Planck constant comes in the definition of the kilo, okay? And this is the NIST balance, the Watt balance that's in Gatesburg, that is actually defining the kilo from the next year on, and there will be many balances around the world, right? So let me explain how this works. Before I explain how it works, I want to demonstrate two principles. One is everything here is based on force and using magnetic field and current. So I'm going to demonstrate to you very fast two different ideas. And the first one is when we have a magnetic field, it's produced by a permanent magnet. And can we flip it? And we come and then imagine that the first situation, which is I have a coil, collection of wires, connect to a voltmeter, and I'm going to approach a magnetic field there. So this is a well-known law in physics, which is the law of induction. When I move a magnet near a coil, I induce a voltage. And of course, this is a closed circuit, but end by having an electrical current. If I go very slowly, this induces very little. If I go very fast, this induces a lot. So there is a relation between induction with the speed of moving the magnet. Another demonstration that I want to do to you is the force. Now, here I didn't have current, I generate current. But now I'm going to have a coil here. The easiest way is having a pendulum because and this pendulum has a coil in it, and I'm going to pass a current through it. So here I have a generator, and I'm going to pass a current. And if I put more current, as you know, I have an equilibrium here. If I have zero current, nothing happens. As soon as I start to have current, a force starts to appear and start to move this from the equilibrium. This is another principle. And it turns out that this force is proportional to the current I use. If I use less current, I go a little bit from the equilibrium. If I use more current, I go further from the equilibrium. And the field is more or less fixed here, this magnetic field, as I indicate to you with that arrow. Okay, so this is the two demonstrations I want to do before continue to what I want to show to you so you're going to understand how everything works. Let's imagine now that we have a magnetic field produced by a permanent magnet like this. So the same red arrow is here. So here there is a magnetic field. You cannot see, but current can see. And what we're going to do is approach it to this region where there is a magnetic field, a coil, the same way I did. Okay? I don't know the magnetic field, and I don't know very well the current. I don't know very well the circuit, I'm sorry. But the circuit here has a length L, which somehow characterizes the geometry of this circuit. So if I do a movement, if I move this coil up, as I am entering the magnetic field, I see a voltage that is produced the same way I demonstrate to you. Because now I'm moving here, I'm moving the circuit. It's the same than moving the magnetic field as I did. And this voltage that's induced depending on the velocity, which is the rate in which I'm moving the circuit to the magnetic field. So this is the voltage. It's proportional to the size of the circuit and the magnetic field and the velocity. Because I showed to you, if I go fast, higher voltage. If I go slowly, small voltage. So I'm going to tell you that all the characteristics of the circuit, the size, how many wires I have, and the magnetic field there, even if I don't know it, it is the relation between the voltage that's induced divided by the velocity. And those things I can measure very well. Even though I don't need to know the field very precisely or the size of the wire in those coils, by measuring this voltage and the velocity, I know precisely this product. Okay, now we're going to do another experiment. We're going to pass a current to this coil, the same coil. Has to be the same, because what I did is I discover a number, voltage, and velocity that characterize completely. Now I'm going to pass a current to this circuit, and when I do, and I put it near the magnetic field, a force will appear. The same way I demonstrate to you, this force is called a magnetic force on the electrical current, depends on the current, the size of my circuit, and the field. But this quantity here, I already defined before. And now I'm going to do something else. I'm going to hang a mass to this circuit. When I hang a mass to this circuit, and then I increase my current until the weight, the gravitational force on the mass equilibrates to the magnetic force. When that happens, I have this equality. But this guy here, I have already measured, which is that voltage divided by the velocity. So it turns out when I substitute everything that and multiply the velocity here, that the weight, the mass times the gravitational, the acceleration of gravity times the velocity is equal to the current that I apply to equilibrate and the voltage that I had before when I calibrate. It turns out that this is the power, mechanical power, is the power necessary to move a mass m in the gravitational field at a constant velocity v. And I times v is what we call electrical power. So when I do this experiment, I am equilibrating mechanical with electrical. And that's why it's called watt, because the unit of power is watt. Okay, so that's why it's called watt balance. And it's not equilibrating mass. It's equilibrating electrical power with mechanical power. Okay, so if we do that, we have everything to define mass now, right? Because we have here G, we can measure precisely, we can have a velocity. Bill knows how to measure length and time very well, he can measure well velocity. And if I can measure very well current and voltage, I have a very well established relation to make everything to be exactly to produce a mass of a kilo. This is the principle of the new definition. Now, the whole question is, how can we measure very well current and how can we measure very well voltage? And to do that, we use quantum effects that community like this one that's in this meeting has investigated. So that's why we're going to do. We have to measure very precisely voltage and very precise current. How we measure very precise voltage? We use a quantum effect that's called Josephson effect. And this is simple. You have two pieces of superconductor, which is a type of conductor that has no resistance, and we make a layer here that will not transmit current. It's an insulator. Yeah. And when we put a current here, we force a current with some specific frequency. And remember, Bill knows very well how to measure frequency, which is the time definition. If we put a current here with a specific frequency, what Josephson discovered is that a voltage appears in this junction. And this is called Josephson junction. And we had some demonstration, but by the lack of time, we're not going to do. And we can show that the voltage is this precise frequency that we know very well, times the Planck constant divided by 2 times the charge of the electron. And this is a constant. So you start to see where Planck's constant is coming. Is the precision on the measurement of the voltage. What we're going to do to measure that voltage that I induce here, we're going to have many of those junctions, and we're going to stack them. We're going to make a series of them until we build up the voltage that I decide I need to calibrate my system. And when I do that, I have an integer number that I call n times this voltage, which is a defined voltage. Okay, so this is how we measure the voltage very precise. But now we have to measure very precise the current. It turns out that measuring current very precise is not a good thing to do. It's better to measure resistance. And if you remember from high school, always we have a circuit which has a resistance, and we apply a voltage, a different one now, a current can appear. So if I know how to measure very well voltage, which I just showed to you using Josephson junctions, and I know how to measure very well the resistance, which is another quantum effect that's called quantum Hall effect that gave a Nobel Prize to von Klitzen. So if I know to measure very well and the resistance has a precise value, and in fact the unity of resistance, or the standard of resistance, is a fraction of, again, the Planck's constant divided by the charge of the electron square. And this comes from the Hall effect. We're not going to have time to explain. But when I combine this, if you put this here, this is another n now, because I'm going to build a voltage, another one, that one to calibrate my system. Now I have another integer here, n prime. And then I have another integer here, that's this fraction. When I combine everything, I can measure very precise my current this way by measuring those integers here, because everything else are constant of nature. Okay, so when you do that, I go back to my relation. Instead of current, I put this. Instead of voltage, I put this. And I end with a relation that relates mass, acceleration of gravity, the velocity I use to calibrate, that Bill promises he knows how to measure very well, use interference and the atomic clock, and the Planck constant. Everything else will be my measurement. How many Josephson junctions I need to construct the voltage are here. The fraction of the Hall effect is here. So if I know very well now the velocity and the gravity and the acceleration of gravity, I can put together this and make this a kilo. How is that realized? Well, I already explained this. We make a balance where we have the coil, equivalent to I demonstrate to you, and we're going to try to produce something that equilibrates a mass that's exactly a kilo. We construct a prototype of the watt balance, which is here. And it is basically like this. I prefer this design here. So this balance has 2 coils, but it doesn't need. You can have 1 if you want, but we have 2. And the balance, see here, I have those coils where I can pass current if I need. And I can put a weight here. This looks like those old balances. And there is 2 modes of operation. In the first mode, we're going to calibrate because I need to, I don't know the field. Inside those coils, I have a permanent magnet, which I don't know the field. And I have a lot of wires in this coil, which I didn't bother to count because my calibration is going to tell me what it is. So we're going to go to a calibration mode. And this is going to start to oscillate. And as it's oscillating, it's measuring the velocity, it's measuring the voltage, and it's averaging for me until it is decided that's done. Inside this here, there is a tiny microcomputer that do all that. And now, when it stops, it says, I know very well the velocity and the voltage I need. So once I know that, I go to the second mode. The second mode, in the first mode, I put a current in this first coil just to make this motion, right? The same way I did there. I generate a force that oscillates, and the velocity here is measured by an accelerometer, and we have it precise. And in this screen that you cannot see very well, it is giving me the voltage and the velocity that characterize my system. Now I'm going to take a mass. I don't know the mass, but I will find out what is the mass. Right? I'm going to put in this part, and now I go to the mode of operation where I'm going to apply a current until I equilibrate the gravitational weight with that force that you saw. So once it's equilibrating, you know, this is, of course, is a one that's made for demonstrations. But there is a green light here that should tell me precisely where I am. When I am there, this is exactly determining the mass. I can adjust a little bit. It's giving 124, 25, it's oscillating a little bit, and actually this mass is 125 grams. Okay? If this was a kilo, I will have a precise voltage and current to put in here to really have the equilibration of 1 kilo. So I could come here and add in mass until I reach the equilibrium, and then I take this and I put in a nice box like that, and I'm going to tell Bill, this is precise a standard of kilo. And that's how we have done. Thank you very much. And Bill, let's continue.
Okay, let's go back to the... So now, with an apparatus like this, the kilogram can be realized to about a part in 10 to the 8th, which is better than the changes that happen to the artifact kilograms because of dirt. And another thing is, using a fundamental constant means that there are other methods for measuring the kilogram that could be used as well. And one of the competing methods involves a nearly perfect silicon sphere. This is a picture of the silicon sphere at the German National Standards Laboratory in Braunschweig. And that's an alternate way of realizing the kilogram. Now, a final part of the story. We're almost done. Today, the ampere is the current which, when you put it through 2 long straight wires a meter apart, would produce a force of 2 times 10 to the minus 7 newtons per meter. It's not a very easy definition to use. And in the future, we're going to redefine the ampere by defining the charge on the electron. And what that means is that an ampere is now going to be a certain number of electrons per second. You remember that in the mathematics that Vanderlei showed, the charge on the electron dropped out. It was in 2e over h, and it was in h over e squared, and it dropped out. So we're still free to define the charge on the electron. And when we do that, that means we have exact values of 2e over h and h over e squared, and that way we can use the Josephson effect and the quantum Hall effect to measure all of our electrical quantities. So this cartoon that Vanderlei showed about how we can measure voltage and we can measure current and resistance using the Josephson effect and the quantum Hall effect, this will be the way we make all electrical measurements in the future. Well, we've got two more units. The mole. It used to be, is today, but won't be for very long, that the mole was the number of things that is equal to the number of carbon-12 atoms in 12 grams of carbon-12. You all remember that from high school chemistry. It's not going to be true anymore. The mole is going to be a certain number of things. In other words, we are defining Avogadro's number. And, whoops, the Kelvin. Today, the Kelvin is 1 over 273.16 of the triple point of water. It's not so easy to get water at the triple point, and it's not so easy to divide it up. Now, we're going to specify the thermal energy of the atoms that make up whatever substance we're measuring the temperature of by defining Boltzmann's constant. The thermal energy of something is the temperature times Boltzmann's constant. So we're going to define Boltzmann's constant and then use that as a definition of temperature by measuring energy. So this is the reform that we have for the new SI. These four new definitions of mass and current, of the mole and the Kelvin. So the French Revolution and the Convention de Mètre brought us the International System of Units. Now, on the 20th of May, 2019, which is the anniversary of the signing of the 1875 Convention de Mètre, we will have the biggest revolution in measurement units since the French Revolution. So in the French Revolution, we had liberty leading the people in this famous painting by Delacroix, and now liberty means that we're going to be free of artifact standards, finally. And all of the base units of the International System of Units are going to be defined by fixing the values of the fundamental constants. And this card has all of those defining constants. Now, we're done with the lecture, and we're very eager to get your questions. We are so eager to get your questions that everyone who asks a question will get one of these as a prize. These are the secret constants that are not legal until the 20th of May, 2019, and you get to get one if you ask a question, and you get two other wonderful prizes as well. So it's been our tremendous pleasure to tell you about the new SI this evening, and we've come to the end, and we thank you very much for your attention.